Okay, yes, thank you, Morten. I will speak about green innovation strategies. Trying to not delay you too much for a coffee break, but still. Let me start with a big picture, because we have to think big and bold when we talk about future for plastics. And this is really the 5 megatrends that shape our future, and you know them, of course. We see changing demographics, we see shift in global powers, we see urban culture growing, and we will all live in cities, it seems, in the future. We see lack of resources, climate changes, and we see big data coming, Internet of Things, computerization and automation that will change our working life. So indeed, what about plastics in this future? Well, we are in the plastics community here today. We are friends of plastics, so we know that we need plastics. We want plastics. They are strong, lightweight, they save food, they save energy, and we will have them in our future lives, definitely. On the right-hand side, I remind you only about the main market segments and the polymer types that we have. You know them all. And you know that packaging is the most, at least in Europe, the largest use of plastics. And the main polymers are polyethylene, polypropylene, and PET, polyethylene terephthalate. But of course, on the right-hand side, you see this, the forecasted growth in global plastic production, the linear growth. If this continues, we will quadruple our plastics production in the next years until 2050. 1,200 million tons of plastics will be produced, and it will be used. And as we know today, plastics has a short lifetime, and it is wasted still as into marine environment, into landfills. Of course, this is not the future that we talk about now for plastic. We think about another future. We talk about another future. We definitely talk about a change in the view of plastics. We talk about plastics in a circular economy, where plastics will be considered a resource all through its life. It will not be plastic waste. That concept should disappear, actually, from our thinking. Plastic should be recycled, used again. And of course, this figure is known to many of you. It's from the Ellen MacArthur Foundation that has really lifted this up on the international agenda, where many big companies, stakeholders, world politicians listen to this. And of course, if we manage to reuse plastic, we will need less virgin resources. And the next question, and what is promoted here, is that to the degree that we need new virgin plastic resources, they could come from, not from fossil feedstock, but from renewable resources instead. And I've circled this, so you will, of course, understand now that this is what I'm going to focus my talk about. I will talk about plastics and renewable resources. Some of you are well familiar with this topic. Some of you may not be so much into it, and I will take you through a brief tour in this. We talked about packaging. So this is the world's 10 largest food brand owners. They are large packaging users, of course, because plastic saves food. They are trendsetters and leaders when it comes to developing technology. And they have sustainability targets, sustainability goals high up on their agenda. And this could mean different things, and does mean different things. It means, for example, less use of energy, less use of water, less carbon footprint, or improving the image. And of course, it means improved packaging for the future. And new raw materials is a part of the future that these companies see. And then comes the next, how does the future look like? I can tell you one thing, there is not one single solution to this. There are many. And the first thing we think about, of course, is the renewable resources. What will they actually be? And we talk about biomass. That is the obvious thinking. We talk about first-generation biomass. This is the easy one. This is carbohydrates, it's sugars and starch. It's not too difficult to convert this type of biomass into building blocks for polymers. Then we have the second generation, little little bit more to get at, but absolutely available. Cellulose, or we call it lignocellulose, so it's cellulose, it's hemicellulose, it's lignin itself. This is coming. It's being used already for some today. And then generation next, third, fourth, the distinction between the generations could be a bit blurred and not that strict. But anyway, we talk about greenhouse gases, CO2, methane. We talk about algae, who are small factories in themselves and produce polymer directly, or oils directly. And also on the lower side, you can see that we have included waste, food waste, for example, used cooking oils, other types of food waste, and definitely plastic waste also. And there is development going on in all these areas today. So it's not so that it's first generation, then second, then the third. No, they're all in parallel. And then you can ask, what are the polymers that we will see in the future? Are they new ones? Are they well-known ones? And I can tell you, it's both. I've tried to make it simple to you on the right-hand side. We can think about this in different ways. We can think about polyethylene and polyethylene terephthalate, PET. Yes, we will have them in the future. In this case, it's just turning black to green carbon, and then it's the same. Same polymer, same technology to make them, same applications, same value chain. It's really drop-in. Everything is ready for them, so they can just come. Then we have new polymers coming to the stage. I've listed them here, PEF. I'll tell you later what it means. PLA, PHA. These are made from green carbon only. We're not used to them because they weren't made from fossil carbon. So they're new on the stage. It's new stuff. And then on the lower, the blue ones, we have polyurethanes. In this case, we exchange black carbon for green, and at the same time, we do a little twist on the polyurethane, so they have a little bit different properties. So it's new stuff also. And I will not talk about biodegradability here. I will instead talk about just the polymers, because if you really see here the color coding, green and blue, yes, they are bio-based, they are not biodegradable. So you see on the application graph that I will not go into details because it's small letters, but you will have this presentation and can dive into it. But you will definitely see that it is not the biodegradable ones that are prevailing. It is not. So I'm done with biodegradables. Just don't expect more in this talk. But I will talk about polyethylene because it is such an important polymer. And you may know this. Green polyethylene can be made from sugar. Braskem in Brazil has done it for years. It's available on the market. It is there. I will take you through a little bit of mathematics. 1 hectare of land, it's the size of a large football pitch, gives you more than 80 tons of sugar cane. This is fermented, the usable parts, down to 7,000 liters of ethanol, converted to 3 tons of ethylene, which is again corresponding to exactly the same amount of green polyethylene. I've even offered you a little bit of chemistry, because what you can see on the lower side, I don't dare to point, but on the lower left, it's glucose. 6 carbons, 6 oxygens, 12 hydrogens. What you need to make ethylene, however, is only the carbons and the hydrogens. The oxygen has to go away, so we lose mass in that journey. But then you have to remember that what we do here, from the left-hand side to the ethylene or to the PE, this is done in days and hours. Nature spent several hundred millions of years to do the same, with the use of temperature and pressure and bacteria, and created oil. So, this green polyethylene has been around for years. It is being used. It is being used, for example, in the renewable cartons from Tetra Pak. But this is not the only way, of course, to green polyethylene. You can choose other raw materials. You can use second-generation raw materials, and this is indeed done by Elopak in their choice. They use green polyethylene or renewably sourced polyethylene from from Savik, and in that case, it is made from used cooking oil, for example. So, we have other polymers, as you know. We have PLA, polylactic acid. Lactic acid, you know, feel it when you exercise. This polymer is naturally born bio. It has never been fossil-based. It was never used from fossil raw materials. There is no point in doing it even, because in this case, as you can see, the glucose, the red oxygens that we didn't need for ethylene, they go along into the polymer. So it's a wise and a clever way of using the glucose to make this polymer. It started off as being advocated as a biodegradable polymer, but now we see that the technology development goes up to more value and performance added polymers. On the right-hand side, this yogurt cup used to be made in polystyrene. Now it is made in PLA. And you can see that strong forces are teaming up. Total and Corbion is actually now, or they have started construction of a plant in Thailand to produce this raw material. Of course, we have to talk about PET, polyethylene terephthalate, the famous example, the one we know. It is made from 2 building blocks. I educate you a little bit in chemistry, sorry for that. It's made of 2 building blocks, terephthalic acid and ethylene glycol. 70% of one, 30% of the other. Used to be made both from fossil raw materials. This PET has a very well-developed recycling scheme, of course. It goes round and round in its cycle. Now, if we take one or both of these building blocks and exchange them for green ones, exactly the same, drop in, what happens? Well, the Coca-Cola flask doesn't know this. It feels the same, it looks the same, it is used in the same way, and it goes into exactly the same recycling scheme. All is the same. So it's really a drop-in solution. But the development goes on, and what is happening now is that the PET, well, we can exchange the T for another letter, a PEF. What does that mean? It means that a very similar polymer, just exchanging one building block with another one that is all green made, gives you a very similar polymer, very similar properties, even claimed to be a bit better, better barrier, better mechanicals, and can be used in exactly the same way, except for one thing. It cannot enter the PET recycling chain. That is claimed, and what we see now is that strong forces in Europe have created a consortium that have been awarded 25 million euros to look into the opportunities for creating a new value chain and even setting up a PEF plant. So, what you have understood already, of course, is that companies do not do this development alone. They team up. They team up with R&D partners, they team up with themselves, and they build strong alliances in the value chains. We see an example here of the Bioplastics Feedstock Alliance with these prominent companies that you can see on the below, encouraging the responsible development of plant-based plastics. It's been around for some years already. And they talk about different bioplastics, as we have now clearly understood, PE, PET, PEF, PLA, and also others that I have not mentioned, because this is just for simplicity, a few ones. Something is going on, and a lot, I would say, actually, is going on also outside packaging. What about the automotive industry? If we look back 80, 90 years, well, actually to 1934, in the World Exhibition in the US that year, Ford showcased a bioplastic car. It was made from soybean-derived plastics. Doors, gear knobs, Dove box compartment. A lot of things in this car was made from these plastics. And on the right-hand side, young designers created this, how should we call it, a beetle car. That was the perfect vehicle to explore the urban jungle. So this is how we will drive around in our urban cities. And indeed, companies like Ford, like Toyota, like Renault, like others, they indeed have a sustainable materials strategy. What goes into the car could be recycled plastics, used fibers, wood in different ways, and bio-derived plastics, and out comes all the bits and pieces and the parts for a car. And Toyota for example, in one of their cars, say that we have 80% of the interior of the car made from this bio-derived plastics. So yes, this is coming. Lego and IKEA, other examples of big guys joining the advanced bioeconomy. What is Lego doing? Well, they have invested 150 million pounds, dollars, still a lot of money, into solving this sustainable plastics challenge. They have put up their Sustainable Materials Center, employing 100 new material scientists. And they aim at exchanging the currently fossil-sourced polymer used in their Lego bricks and their Lego toys, currently an ABS polymer, if you'd like to know, with new renewably sourced polymers. And also in the packaging, they are looking for alternative materials. IKEA claims leadership in commercializing bio-based plastics for their purposes, home furniture typically. And they team up with different companies. They go in different directions, it appears at least, when you look to what they're doing. Team up with companies who actually make polymers from methane in bacteria. New technology, really biotech, to make polymers. You can see on the lower left picture, this is actually ready-made polymer in the bacteria. It's there for the taking. It's, of course, requiring some technology development, but it's another way of making plastics. And they team up with Neste and build on the biofuels technology that that company has. So there are a lot of opportunities, a lot of teaming ups. Last raw material I will talk about is CO2. It's fantastic that you can take this troublemaker in our world today, look at it as a chemical, and you can turn it into polymers. You can exchange some bits and pieces in polymers today, some raw materials, by using CO2. It is done today. It is done by the help of catalyst technology. The company Covestro is forerunner in this area, making new polyurethanes with this type of polymers from CO2. Repsol have announced their pilot plant. Saudi Aramco has acquired some technology for this and is pushing this. And of course, indeed, in this room, we have Iconic Technologies who will tell much more tomorrow about their exciting technologies to do this. But this is really an alternative raw material. And of course, that takes me very nicely over to Norner and what we have done in this field. And my last few slides will really give you some examples of what we are doing in Norner. We are doing these projects with you, our clients, of course, and our R&D partners. I have not mentioned any of you specifically by name, but you will recognize yourselves in some of these slides. So it's a pleasure to show these. Yes, Norner has 10 years of experience in making polymers and polyols from CO2. We do it in our lab. This guy here and others before him have done that. We have demonstrated that these polymers, not that easily available, but we can use them. We can make articles, and we can demonstrate that, yes, there is a potential. And of course, the next step, what we need to do, is to take the process technology one step further and demonstrate in a lab-scale pilot that we can do this. On the right-hand side, I've been bold enough to put up the sustainability goals from the UN. You need to think big, be patient, and keep your eyes on the prize that is there in the future. New raw materials and new processes. We work with other raw materials also. We work with lignocellulose, which is a new raw material really for polymers. We do it in different ways, in different projects. You can deconstruct the whole lignin, make new monomers, and build new polymers. We do that. We work with lignin and with cellulose and different types of lignins and different types of cellulose, and work with them as fillers in polymers to make composite materials. We deal with waste, or shouldn't say waste, I should say different types of rest raw materials. From the food industry, for example, we can make mulch films ready to be sprayed on and then plowed down again. So this is an example where you really could use biodegradability. We turn fish waste into sustainable polymers. This is again the bacterial technology that I talk about. We don't do that certainly in Norner. We don't have bacteria in our cupboards. Don't have to think about that. But it's done with partners. And the polymer is again made in these bacteria. But we are the polymer experts, and we see how can we treat this polymer, use it, make useful articles of it. And of course, for us in Norner, what could be more natural than taking plastics waste and consider this not a waste, but really a resource? We can turn that into pyrolysis oils with different boiling points, being used or suitable for fuels of different types. And we do this in our lab today, even, and we will develop this more. And the last example of a project that I will show to you is this one. It's FuturePack. It's a new large project, 4 years, with 10 industry partners from Norwegian industry, with 4 R&D partners, and it actually comprises all the aspects of the circular economy. The big questions to the plastics: where do you come from? Well, bio-based raw materials, possibly from plastics that cannot be material recycled. How is it converted to useful building blocks and to polyethylene and polypropylene, the polymers that we are focusing on? Well, in a pyrolysis process. New technology that has to be developed for these kind of raw materials. And how can we make sure that the plastic does not end up as waste, but it is used and reused, recycled, not even downcycled to lower grade products, but recycled? Well, that is by clever design of packaging. And this is what we will show hopefully in the next 4 years, and I really hope that I will have exciting results to present to you later when we meet. I may have been speeding in my speaking, but anyway, I'm already at my last slide. I'll try to give you some examples of green innovation technologies. I've talked about polymers from a variety of sustainable raw materials, and diversity is really the key word here. Different raw materials, different polymers, different technologies, different strategies. The low-hanging fruits, as you have seen, is drop-in solutions, PE and PET. In the next wave, new polymers requiring new value chains will see the daylight. And bio-based packaging has paved the way, but beyond packaging is certainly on the rise. We see strong industry alliances in the value chains, and we also see indeed strong alliances with R&D companies. And Norner, of course, we take an active role in this development with you, our clients, and with partners, and we drive this sustainability plastics development. Thank you.